Hello everyone. In this video we are going to draw the root locus plot for a system given with the following transfer function: s plus 2 to the power of 2 over s plus 1 to the power of 4. The controller is in the form of a proportional controller, and as usual we start by forming the loop transfer function L of s, which will be equal to kp times s plus 2 squared over s plus 1 to the power of 4, and this is indeed equal to rho times n over d. So rho is equal to kp, n of s is equal to s plus 2 squared, and d of s is equal to s plus 1 to the power of 4. We can conclude that for the system n is equal to 4, we have 4 poles, m is equal to 2, we have 2 zeros, and r, which is equal to n minus m, is equal to 2. This r means that we have 2 asymptotes, for which we need to find out xa and kca, and we will do it soon. Okay? So we have 4 poles, all the poles indeed, s1, s2, s3, and s4, all of them are located at the point -1. And we have 2 zeros, both of them are at the point -2. So we have multiple poles at the same location and 2 poles at the same location. Let's start by preparing the empty graphs for our positive locus. And negative locus. We can start by drawing the location of the open loop poles and zeros of the system. Again, we have 4 poles at the point -1. If this is point -1, we have multiple poles there, and we have 2 zeros at the point -2. So we have our poles and zeros for the open loop system drawn here. Just keep in mind that we have 4 poles and 2 zeros. Now we can start to, let's say, by finding out the values for the asymptotes, xa and kca, and then drawing the asymptotes. For xa, we know that it is in the form of sum of zi's minus sum of pi's over n minus m. For sum of zi's, we have 2 plus 2 minus, for sum of pi's, we have 1 plus 1 plus 1 plus 1. And the n minus m is equal to 2. So we'll get 4 from here, 4 from here, 4 minus 4. So we will have xa equal to 0. The point of abscissa, xa, will be located at the origin. For kca, we have r times kca equal to 2h plus 1 times pi for positive locus and 2h pi for the negative locus, where h will be equal to 0, 1, 2, 0 and 1, because we have only 2 asymptotes. Okay, so h will be equal to 0 and 1. Therefore, we will have 2 kca equal to pi and 3 pi, 0 and 2 pi. For positive locus and negative locus. And then we will have kca equal to pi over 2, 3 pi over 2 for the positive locus, 0 and pi for the negative locus. with xa equal to 0, we can draw the asymptotes. So for the positive locus, we will have these two asymptotes, and for the negative locus, we will have one asymptote starting from the origin and going towards plus infinity, and the other one will go towards minus infinity on the real axis. Alright, so we are done with the asymptotes. Now we can have a look at the parts of the real axis that belongs to the root locus. For each case, we can segment the whole real axis into a part from minus infinity till minus 2, from minus 2 till minus 1, and from minus 1 till plus infinity. We can count the number of the poles and zeros on the right hand side of the segment. From minus infinity till minus 2, we have all the poles and zeros, so the number will be equal to 6. From minus 2 till minus 1, we have 4 poles on the right hand side. And then from minus 1 till plus infinity, there are 0. And you can see that none of them are indeed an odd number. Therefore, all the segments will belong to the negative locus. The real axis doesn't belong to the positive locus at all. So the whole real axis will be part of the negative locus. Our branches will not lie on the real axis for the positive locus. Another thing that we know is that the branches will originate from the open loop poles of the system. 2 of them will end up at the zeros, and the other 2 will move towards the infinity. So therefore, we will have, for the positive locus, I think it is kind of obvious, we will have break away points right at the point minus 1, because all the branches will go out of the real axis at this point. They cannot lie on the real axis, and since we have 4 poles, there will be 4 branches going out. 2 towards the positive imaginary values and 2 towards the negative imaginary values. Out of them, 2 will approach the infinity using the asymptotes that we have here, so somehow like this. And the other 2 will approach the zeros, the 2 zeros that we have. So the approximate root locus plot for the positive locus will be something like this. What we need to find out here is the angle of departure, alpha departure, and the angle of arrival. If we find those two, we will be kind of done with the positive locus. Regarding the negative locus, on the other hand, we have again 4 poles at the point minus 1. Okay, let me see which color would be the best. So one branch will originate from one pole at minus 1, and it will move towards plus infinity, okay, using one asymptote that we have here. One branch will move on the real axis towards 1, 0 at the point minus 2 on the real axis. On the other hand, we need a branch to approach the second 0, and it will be on the real axis because that part of the real axis belongs to the root locus. We have 2 more branches that needs to be departed from the point minus 1. So they will move somehow in this way. So there will be a breakaway point at the point minus 1. At some point they will enter the real axis. One branch will move towards the 0 at minus 2, and the other one will move towards infinity using the asymptote. So for the negative locus, we will have the break away point at -1 for sure, and then there will be a break-in point that we need to find out. Break-in point, and we don't know where it is, okay, for now. We can also find the angle of departure. Angle of arrival at the zeros is kind of obvious in this case. They will be equal to 0 and pi. But we can still have, use the formula that we have and determine or verify those values. Alright, so let's start by finding the angle of departure from the poles. So alpha departure. If we look at our poles and zeros, we have 2 zeros at the point -2, and we have 4 poles at the point -1. So over here, and we want to find out the angle of departure from the poles at -1. So for us, Q is equal to 4. We have 4 number of the poles there. To find out the angle of departure, we can simply apply the phase condition. Phase of n minus phase of d is equal to phase of -1 over rho. And we set a point pretty close to test point, pretty close to the poles. So we can call it S star. We evaluate it at S star. For the zeros, in order to find out the phase contribution, we connect the 0 to that point, the test point. We draw a horizontal line from the 0 towards +infinity, and then find out this angle over here. And since the test point is pretty close to the poles, this angle will be 0 degrees. Okay, so the contribution coming from the zeros will be equal to 0 radian or 0 degrees. Then regarding the poles, we take the same approach. We connect the poles to that test point, draw a horizontal line towards +infinity, and then this will be indeed our alpha departure. But since we have 4 poles over there, we will have 4 times alpha departure. So basically we have -4 times alpha departure being equal to 2h plus 1 times pi for the positive locus and 2h pi for the negative locus, where h will be equal to 0, 1, 2, and 3. Because we have 4 poles. So alpha departure will be equal to, if we plug the values of h from 0 to 3, we will have minus pi over 4, minus 3 pi over 4, minus 5 pi over 4, and minus 7 pi over 4. And for the negative locus, these are for the positive locus. For the negative locus, we will have 0 when h is equal to 0. H equal to 1, we will have 2 pi over -4 or minus minus pi over 2. Then we will have minus, if h is equal to 2, we will have minus 4 pi over 4 or minus pi. And finally, when h is equal to 3, we will have minus 6 pi over 2, which is equal to minus 3 pi. And this is for the negative locus. Let me see if I did everything correctly. For the negative locus, let's do it again. Alpha departure will be equal to minus 0 over 4, h equal to 1, we will have 2 pi over 4, 4 pi over 4, and 6 pi over 4. So we'll have minus 0 pi over 2, pi, and 3 pi over 2. This isn't okay. So minus 3 pi over 2. Alright, so now we have the angle of departures for our pose. If we look at the positive locus, drawing that we just started, the branches will depart with the angles that we have found. So minus pi over 4, minus 3 pi over 4, minus 5 pi over 4, and minus 7 pi over 4. These will be the angles with which the branches will depart the pose at the point minus 1. On the other hand, for the negative locus, we have found the values to be 0, minus pi over 2, minus pi, and minus 3 pi over 2. Two of them are kind of obvious. We have 0, minus pi, and these two will be also depart the branches with the angle of minus pi over 2 and minus 3 pi over 2. So we are done with the angle of departure. We can now focus on finding the angle of arrival at the zeros. If we call them beta arrival, we have 2 zeros at the point minus 2 and 4 poles at the point minus 1. To find out the angle of arrival, we set a test point pretty close to the zeros and then apply the phase condition. So phase of n minus phase of d is equal to phase of minus 1 over rho. For phase of n, we connect the test point to the 0 through a horizontal line from 0 towards plus infinity, and this will be our indeed beta arrival. And since we have 2 zeros, we'll have 2 times beta arrival minus, for the pose, we connect the test point to the pose through a horizontal line from pole towards plus infinity, and then this will give us the angles theta I. And since the test point is pretty close to the zeros, it is pretty close to the real axis, and therefore the theta i's will be equal to pi. So minus 4 times pi, as we have 4 poles over there, is equal to phase of minus 1 over rho. So 2 times beta arrival is equal to 4 pi plus 2h plus 1 times pi for the positive locus, where h is equal to 0 and 1, and 2h pi for the negative locus, where h is equal to 0 and 1. Therefore, beta arrival will be equal to 2 pi plus, if h is equal to 0, we will have pi divided by 2, we will have pi over 2, and 3 pi over 2, we'll have 0 and pi. And obviously we can neglect 2 pi, so beta arrival for positive locus and negative locus will be equal to pi over 2 and 3 pi over 2, and 0 and pi for the negative locus. For the negative locus, it's kind of obvious, as we already had started to draw it. We can see that we have the branches approaching the zeros on the real axis, so we have the angles equal to 0 and pi. For the positive locus, we have obtained the angles of arrival equal to pi over 2 and 3 pi over 2. So these angles will be equal to 3 pi over 2 and pi over 2. So the branches will enter into the zeros with those angles. So we will have something like this indeed. Okay, now we need to find out the break-in point in it. In order to find out the break-in or break-away points, we can refer to the formula that we have. So we break in and break away point. You know that we should apply m prime d minus d prime n equal to 0. For n we have s plus 2 squared, and for d we have s plus 1 to the power of 4. So n prime will be equal to 2 times s plus 2, and d prime will be equal to 4 times s plus 1 to the power of 3. If we plug these values into our equality that we have here, we will get 2 times s plus 2 times s plus 1 to the power of 4 minus 4 times s plus 1 to the power of 3 times s plus 2 squared equal to 0. Then we can simplify it by removing s plus 2, which will give us s1 equal to minus 2 as a break-in or break-away point, and then taking s plus 1 to the power of 3 out as well. And that will give us s2, 3, and 4 equal to minus 1. The remaining will be equal to 2 times s plus 1 minus 4 times s plus 2 equal to 0. If we simplify it, we will have 2s plus 2 minus 4s minus 8 equal to 0, and this will give us 2s equal to minus 6 or s equal to minus 3. And this is the break-in point that we were looking for. So this point, break-in point, will be at minus 3. Now that we have kind of all the information, we can maybe redraw the plots again. Let's start by preparing the empty plots for positive locus and negative locus. For poles at minus 1, 2 poles at minus 2, 2 zeros at minus 2. For the negative locus, the angles of departure from the poles are pi over 4, 3 pi, 5 pi, and 7 pi over 4. And the angle of arrival at the zeros are pi over 2 and minus pi over 2. So we will have something like this. And then we had the asymptotes with the angles of pi over 2 and 3 pi over 2 with xa equal to 0. So that's what we get for the positive locus. For the negative locus, one branch will go towards plus infinity, the other one will move towards the 0 at minus 2. Then two branches will depart the real axis with the angle of pi over 2 and minus pi over 2. They will break in to the real axis at the point minus 2, so we will have kind of a circle over here. Then one of them will go towards the 0 at minus 2, and the other one will go towards minus infinity on the real axis. Okay, so we are done indeed with drawing the root locus. You can also have a look at what we get by applying the rlocus command of MATLAB. So here we have the positive locus and the negative locus. And you can see that what we have here is kind of the same as what we have obtained by doing it manually. Apart maybe from the scaling and exact drawing things. Okay, so then we need to find the range of values of Kp in R such that the closed loop system is biboy-stable. And we will directly use the magnitude condition instead of the Roth criterion. We don't refer to the Roth criterion here. If we look at what we have obtained, we can see that for rho bigger than 0, or Kp bigger than 0 in this case, we have our system biboy-stable. And for negative values of rho, up to some point our system will be still stable, but right at this point, right at the origin, the system will become unstable. So this is a critical point for us. We can figure out the exact value of rho over here by applying the amplitude condition. Amplitude of n over d is equal to the amplitude of minus 1 over rho, and this will give us the value of rho. For amplitude of n, and we know that the test point for which we are applying the amplitude point is s equal to 0, amplitude condition. So this will give us, for the numerator, we will have 2 times 2, or 2 squared, and for the denominator we will have 1 to the power of 4, which is indeed equal to 1, and this is equal to minus 1 over rho. So amplitude of rho will be equal to 1 over 4, or 0.25, and since we are in the negative locus, rho will be equal to minus 0.25. So we would say that for rho is smaller than minus 0.25, the system will become unstable. But if the rho is bigger than minus 0.25, the system will be biboy-stable. And in total, if you consider both negative locus and positive locus, we would say that for rho, which is equal to Kp bigger than minus 0.25, we have the system being stable. Otherwise, it is unstable. And I think we are done with this example at this point. Okay, so thank you for watching this video, and see you in another video later.